Unfortunately, I'm hearing an echo, which is not too good, but I can do the best I can. By the way, title is, will the real sea level please rise? Well, guess what? Take a look at that picture. Is the sea level? Not at all. So here are the sources of sea level rise. Not necessarily in order of importance. I could be talking about each of these. Model magic, thermal expansion, how we measure things, and worst computational errors. And then land-based ice melt additions, which I'm going to have to sacrifice because I wanted to show that movie. So let's take a look at suppositional model magic. Here's claims beyond belief, number one. Now, Arthur Gordon MacDonald testified to Congress since 1979, and then on the steps of the Capitol, predicted sea level by the year 2020. This was published all over the country in Discovery magazine. Guess what? It didn't even get to the laces of his shoes. This is 2020, by the way. So that's one wrong prediction. And let's look at what James Hansen did. He testified in 1988 that we were going to get 5 meters, 16 feet of sea level rise by the end of the century, by the end of 2100. He saw pretty quickly that that wasn't going to happen. So then he changed his tune. He said, oh yeah, we're still going to get to 5 meters. However, we're going to double it every 10 years exponentially. You notice by the time 2060 runs around, he's long gone. His prediction will, quote, not be disproved. And yet he still says we're going to be heading up 16 feet by the year 2100. Well, one of the world's greatest oceanographers, Niels Axel Mørner, studied what Hansen did. And like Hal Dwarren, our former chairman, he put a maximum possible limit. Hal did it for CO2, Mørner did it for sea level. And he said the maximum possible, if the rate of ice melting and thermal expansion all come together, it cannot be more than 10 millimeters a year. Now, if you notice, look really close at the bottom of this slide. You see that red dot? That's where I'm predicting sea level really will be. That is the 50% probability of sea level either being higher or lower than that red dot. Now I'm going to talk a little bit about oceanic thermal expansion. Now we all know that the upper layers of the ocean expand when heated by the sun. And I'm going to talk about this giant flying boxcar that the Europeans put up. It's called ENVISAT. About 18,000 pounds, largest satellite ever put in orbit. And by the way, they never reach above 480 miles. They're low Earth orbit. And that allows some accurate sea level measurement. Here's ENVISAT in the laboratory before it was launched. And this is how it actually calculates the sea level. And it uses the geoid, the ranging radars, and actually achieves sub-millimeter resolution. Let me show you what that looks like. You notice there is a 2 centimeter, not millimeter, difference in sea level rise on an annual basis around the world. Now you notice in the middle of each year, between 2005, 2006, 2007, 2008, in the middle of the year, sea level actually drops. In the winter months, it peaks. Now, why does that happen? Again, we have sub-millimeter resolution. This is damned accurate. This is the winter view of Earth. It's all ocean from the satellite. So the sun shines on the Earth. You notice the ocean is dark. The ocean absorbs that solar energy. And yes, thermal expansion heats up the upper layers of the ocean, and that's where you get that 2 centimeter difference. Let's look at this. We have, Earth is one ocean, but we're measuring it in different ways. And I'm going to talk about how we are able to do that. This is GPS. It's actually what I call CGPS, which is co-located GPS. What you do is you take a GPS station and you match it and link it to a tide gauge. And this is the OD Newland. It's near Cornwall in England. And ODN, Ordnance Datum Point Newland, is the datum for the entire British Isles, co-located GPS. So the GPS measures subsidence at Cornwall at 0.7 millimeters a year. The sea level rise recorded there, according to the graphic, is 1.8 millimeters. The net rise in a validated, measured GPS located tide gauge is 1.1 millimeter a year. Now, by the way, in that graphic, you see a green line showing CO2 increasing. Well, guess what? The sea level at Newland in the UK has been linear for 100 years, and trust me, it's going to keep going that way. Now, GPS works on the west coast of the United States. You notice Alaska is experiencing uplift. You can look at the color coding on the graphics. While the California side, due to Pacific subduction, is actually slightly sinking. Right in the middle, in between the West Coast subduction and the Alaskan uplift, is Prince Rupert, British Columbia. They too have a co-located GPS that's been there for over 10 years. We can verify and validate sea level rise because of that. So here we have Prince Rupert, British Columbia. They have a subsidence of 0.07 millimeters a year. They're recording 1.17 millimeters a year. What's the next rise? 1.1. And again, superimposed is the CO2, but the trend is decidedly linear. It's a drop, by the way, in 2011 to 10. I'm going to talk about that in a minute. Take a look. This is all over the world. This is not every tide gauge, but my goodness, if I expand this, it doesn't make a difference. They are all linear, straight line change. Some are going down, some are going up, depending on local tectonics. Now, this is Slipshaven, Denmark. Slipshaven, Denmark is also in Europe, and it also is between the great Norwegian uplift and the Low Countries sinking. But in that area, it's 1.03 millimeter rise a year, straight line, linear. Next slide, please. CO2 does not affect it. So I ask, is CO2 a major driver of the coastal sea level rise? It may drive the IPCC's models, but it plays no role in worldwide coastal sea level rise as measured by tide gauges. So the IPCC is saying, hey, this is what's going to be happening with sea level rise. And you'll notice, by the way, in the current US National Climate Assessment, this rise starts in 1992. Remember that date because we're going to be talking about it later. And these are all off the wall, off the charts. Sea level by the tide gauges is still linear, hasn't changed, and yet they're talking about 8 feet of rise by the end of the century. This is a chart from the Netherlands. It's in Dutch, but it also starts in 1992, and they're also projecting a rapid sea level rise along the Dutch coast. Guess what? It's not going to happen. This is a mantra at NASA. You measure the measurements, you measure, you calibrate them, you validate them, and I left one term here, you verify them. And we're going to be talking about verification later on. My NASA colleagues are all familiar with "In God We Trust, all others bring data." Well, I'm bringing you data. This is a history of sea level rise. Now, by the way, the sea levels measured on these charts are verified and validated through geological evidence, not models. And you can see the whole list of places in the world where we've measured them. We've had 140 meters of sea level rise since 2,000 years ago. You notice most of the rise took place during a 7,000-year period. That's an incredible rise in 7,000 years. And then it levels off. The chart on the right shows you where it levels off to. During that 7,000-year period, there was a meltwater pulse. It basically dumped out the giant Lake Bonneville and dumped it into the Snake River once an ice dam broke. Lake Agassiz followed too. And by the way, I want you to look at these rocks. These are photographs I took along the Snake. And by the way, on the left rock there, you see some petroglyphs. We can date these rocks very accurately. When Lake Bonneville dumped out thousands, no, tens of thousands of these round rocks rumbled down the Snake River. That's some of the petroglyphs on the rocks. There you see hundreds of rocks here. Along the Snake, there are tens of thousands of these. When that giant lake emptied out, rolled these rocks down the river, and a Snake went all the way into the Columbia and out to the Pacific. This is a huge, giant meltwater event. Here we go, back to all that 7,000. You can see where that meltwater pulse is. Maybe I can show it with my cursor right here. How you like that? Okay. Jim Hansen is telling you that in 80 years, we're going up 16 feet. And this trend line, by the way, represents a satellite trend line. I'm going to talk about that later on. We have to invent new laws of physics to add those 5 meters in the next 80 years, when over 7,000 years, we had very little rise. This is a tide gauge. This one happens to be out in Fort Point, New Hampshire. It's anchored to the bedrock. There's a monitoring station. Tides vary a lot in Portsmouth. Tide gauge is very accurate. But there's a bias in tide gauges. Why? People put tide gauges where they believe that the sea is rising, which means the land is falling. So if you average all the tide gauges, it's going to look like sea level is really going up. But it's not. You have to look at the individual ones, and especially the ones that are in tectonically inert areas. These are Europe tide gauges. They have all have 80 years or more records. Lots of them are in the area of transition here. Holland sinking, Norway rising, Denmark right in the middle. This is what isostasy is all about. You put 2 or 3 miles of ice on top of land, it pushes down the land into the asthenosphere. On the edges, you have what are called a forebulge. That's the current day Netherlands. These are tectonics in the Baltics. The highest rise, 800 meters in central Norway. Down here in Holland, the Netherlands, sea level is rising 170, which means the land is sinking. Right in here is the tectonically inert zone. This is a close-up of that tectonically inert. Here is a zero line, and what we want to do is look at the sea level on that zero line. And this is Slipshaven, Denmark. It's, again, totally linear. CO2 going up, 1.02 millimeters a year, over 100 years of record, no sign of acceleration. Now, there are some places in the world where NOAA is declaring sea level is rising like crazy. Well, Seward, Alaska is one of them. The red line shows the sea level rise line claimed by NOAA. And it's quite huge. But this is not true. What happened in Seward is in '64, they had an earthquake. Seward dropped. Sea level before was slightly falling. Sea level after the earthquake, right here, is also falling. The trend in sea level is still falling, mainly because it's in Alaska, where Alaska's land is rising. And it's still linear. There is no upward trend in Seward, Alaska. Oh, by the way, I contributed to a paper that was published in 2019 that I co-authored with Nils Axel-Murner and Albert Parker, where I go into real detail about the Seward, Alaska earthquake and the effect on sea level rise. I'm going to send a link to it to Jim Peacock, and if you guys want to download the paper, it's published in an oceanographic journal. So let's go to the next one. This is computational errors. The Americans put up the Topex, Poseidon, Jason satellites with France. And we're doing it for medium orbit. That's 800 miles up. It's higher than ENVISAT. So it's not that accurate. This is what you're still looking at linear sea level rise, but the rate is way higher as measured by these satellites. The latest, still linear, big drop in 2010, which validates some of the other slides. This is Prince Rupert, BC. You see the difference between the satellite readings from Topex, Poseidon and the real readings by tide gauge. This is the resolution issues. Topex, Poseidon does not have a sufficient resolution to measure at the 1 millimeter level. It has 2 orders of magnitude, almost 3. They can't do it. Why do they use 2 radars? It turns out that the C-band, which has an even lower resolution, is very good for penetrating clouds. Roy Spencer supposedly posited that the clouds are a problem. He's correct. This is the problem. Clouds are filled with little ball lenses. A ball lens reflects 5% of the incoming light, transmits 95%. So you see, as that attenuation goes down to the cloud, the bottom gets really dark. The problem with the satellites is they have 2 radars, but only 1 antenna, and they have to pick which one. So when they're flying over clouds, like over here in the Central Pacific, they have to switch to the larger, low-resolution waveband in order to get a good, accurate reading. I'm going to skip the GIA because there's some detail here, but I'll handle looking questions if there are any. Now, here's the big slide. What happened in 1992 that forever changed the direction of sea level rise as reported by that satellite? Did we get hit by an asteroid? Did we change our orbit? None of that happened, and yet the sea level rate changed. And by the way, that little red arrow there, that's where the real sea level ended up. This is an IBM 340 mainframe. It's the kind of computer that I worked on at NASA. What you do, these mainframe computers could do one thing really well. They could add. So when you made a subroutine in machine language, you basically forced it to add, and add. So you take the sum of the C band and the KU band, you add it to itself 5 times. Again, adding. You shift the decimal 1 place left, and you have effectively multiplied the sum by 5 and divided it by 10, which is really dividing it by 2. And it's precise, not subject to error. However, they use a higher level language at the University of Colorado to analyze these radars. They added them together, but they forgot to divide by 2. Or they put the number 2 in a register, overrode it by a 1, and then declared that as being the average. You have 2.9 millimeters a year reported by the satellites. You've doubled the radar, not averaged it. You knock out GIA by 3 millimeters, and you get exactly the same worldwide sea level rating, 1.15 millimeters a year. And that takes you to the red arrow that you see on the right. This is the real sea level, not what you see reported here, because this is a computational error and the University of Colorado should be penalized for it. This is the slide you need to remember. Science is not complete when you thankfully achieve the result you were expecting, and they were expecting sea level to go up. You have to measure, calibrate, verify, and most important, validate it to other measures that we know are hard, solid data. They did not do that. Next slide, please.
The attribution of sea level rise, what percentage of that is thermal expansion since the end of the Little Ice Age, and what percentage is, say, melting of the ice caps or some other source?
Well, the fact is, if you look at the last graphic of sea level rise, that is the exact sum total of all the thermal expansion, all the ice melt, and any other change we have in sea level rise. And it is linear, it is unchanging.
Yes, I'm not questioning that. I'm just asking can you explain the sea level rise to be predominantly due to thermal expansion, due to the warming of the oceans since the Little Ice Age ended?
No, it's actually more land ice melt slowly adding to the oceans, but the ice melt is melting at a very linear rate. Greenland is increasing its interior ice depth, and it's decreasing the edges where they're spilling into the sea, but it is linear. The same is true as Antarctica, but Antarctica actually has a net increase in balance, as demonstrated in the Zwally paper.
Okay. So the sea level rise doesn't support the hypothesis of net melting of the ice caps at an accelerating rate right now.
Now, keep in mind, the floating ice in the north, in the Arctic, is not going to raise sea level at all because it's already displacing all the water that it does. And it melts and refreezes annually with no real effect on sea level.
That's basic physics. Tom, thanks very much for taking time. Joel?